And the current NoScript versions actually already support external filters. At this point, I would really like to thank Giorgio, because normally if you try to work with someone else and suggest that they change their stuff so it supports your stuff, it takes quite a lot of convincing or throwing money at it. In this case, he was really responsive. He was right up to the idea and invested quite some time, and yeah, he should actually serve as an example to many others how to actually cooperate in a security space. This is how it looks like. You just in the NoScript options, you now have an external filters tab where you can, you just say where the executable for Blitzableiter is. You can turn on and off the filtering for individual sites. So it's the UI flow is the same as everything else in NoScript, so it doesn't require any learning on your side. It should actually simply work. The integration into websites is also a fairly trivial thing, since it's a command line utility. You can just put it behind your upload form and check the return value. If the program exited with 0, then everything is fine. Otherwise, the file was evil. And we're considering offering a SOAP or XML RPC or whatever servers so people can use that. But we haven't built it yet, because we're actually we want to see what the feedback on this is, whether someone actually wants to use that or not. Blitzableiter is open source. It's GPL v3. The main reason behind this is because I believe that Kerckhoffs's principle from cryptography, which says that everything should be public except for the secret key, so the algorithm and everything should be open, should also apply to defense mechanisms and security mechanisms. I don't want to believe in yellow boxes that, the people promise they will make me secure and them rich, and usually it only fulfills the second requirement. I believe that if you have a security tool, you have to be put into the situation of verifying how much security it actually provides to you. Also, we want to see the code integrated into other tools that have to deal with Flash, and we love to get bug reports. The website is down here, blitzableiter.recurity.com. And there's public issue tracking. You can file bugs against us, and you can see how we perform fixing them. Yeah, so we have a demo time, which means all shit goes wrong now. Let me see. So there is my very minimal version of the internet. So let's click on a link. You see, this is what NoScript usually does, is it prevents Flash from actually happening. Now, if we choose to actually see that piece of Flash, it will load it eventually, and yeah, there it is. It's just a glass of martini. Not that I'm particularly fond of martini, but didn't find anything else. Now, if we actually use an in the wild implementation of a very recent exploit, we do the same thing. Please hack me. Schnupp, schnupp, schnupp. It should actually do something. I hate demos. Sorry. So what happens is, see, I'm not used to multi-monitor setups, so I didn't look at my screen. So what happens is you get a pop-up that says essentially there was a difference in the stream length from the decompression and what the header declared. So that is in the very first bytes of the Flash file. Most exploits actually never bother to set the length fields correctly, And this is what happens here. So that's in the wild exploit, and it was essentially eaten, and then you get this. Or you can configure whatever replacement file there is. You can also like flip a finger or something. This is the new function, long argument. That's relatively recent exploit that wasn't public, but I figured out how it worked and wrote one myself. That one actually has correct length fields. Now we have the same thing again, that the window pops up here. So here you see that it actually, in the verifier, figured out that the index of the method is out of bounds, and so rejected the file. So much for the demo. Is anyone impressed? So, excuse me? I don't know. So this is essentially what you get. Now would be the right time to switch talks. Let's dive into the Flash format a little bit. Flash files, or so-called SWIF files, are specified from version 3 to 10. Everything is still supported. There is another quote that I like in this context: is trying to maintain backward compatibility is like trying to stay close friends with all your ex-girlfriends. We all know how well that works, and the same can be said about Flash. I mentioned that Flash can be compressed using zlib methods. There's a type length value structure thingy that they call tags. They're the main container elements. There's 63 of them defined or documented for version 10. And the data structures are extremely version dependent. So the same data structure actually looks different depending on what version the Flash file claims to be. When you look at those tag types, there's control tags that do simple things like setting the background color, or labeling stuff, or ending the Flash movie. Then there's display list tags that define and show graphic elements. You already see they're called like place object 2, place object 3. That actually doesn't mean that the second will actually place 2 objects. It's Adobe's second attempt to get it right. And then there's, the third attempt to get it right, and so on and so on and so on. They also do that with the opcodes. But of course, they still support the first version. There's bitmap tags, so you have JPEGs and BMPs and all that type of stuff. And then they have a special thing, a special graphic object they call a button. There's, again, a defined button and defined button 2. And a couple of other things, and they're used for interactive programming. So if you click on stuff, then stuff should happen. When you look at one of those tags, here's one that is called define scene and frame label data. They're often, like, every tag has its own data structure. Like, none of them are like close to each other. Everything is its own data structure. They're often composed of many sub-data types that are then composed into lists and with counters and all types of interesting things that can very well go wrong. Very nice places for integer overflows and the like. The tag you see here to the right is actually the one that caused CVE 2007-0071. Because if you look at the scene count here, where's my mouse pointer? If you look at the scene count here, it's a 32-bit encoded number, and this one could be negative, and then it essentially overflowed. So how do we want to prevent this from happening? What we do is what I call normalization through recreation. So essentially, we parse the Flash file safely without getting owned ourselves. Then we actually throw away the original file and use all the information that we gained from the original file to create a new one. And the new one is then well formatted and can be fed into the more fragile the more fragile consumer, in this case the Flash player. Very simple concept. The thing is, we have to actually implement a pretty much secure parser in order for this to be helpful. So what we did is we use managed code strictly within .NET. This allows us to define buffers and memory regions that we work on, and then have the CLR take care of whether we have out-of-bounds reads or integer overflows, which would otherwise be very, very tedious and error-prone to check manually every time. So we leave that to the CLR. We can actually load the individual TLV data blocks into individual memory streams, so every time we have an outside reference, we will catch that. And with this approach, we can also see if we have trailing data or if any of the length fields are not correct and stuff. We only accept well-documented data structures. So if there is an undocumented data structure, that we're going to reject that. The downside of that approach, of course, is that we actually have to parse everything in the file, which requires a shitload of code. If you're willing to download the source code, you will discover that it's a couple of megabytes, and that's pretty much all parser code. We also verified version dependencies of the data structure, so if you happen to use a data structure that is only defined for version 8 and above, and your file declares to be version 6, we're going to complain about that. And here's an example why using .NET for this task is actually quite smart. In my opinion, this is what happens when you read a CVE 2007-0071 exploit. It will right here where the negative scene count, where's my mouse pointer? Where the negative scene count is, report an integer overflow exception, and then it will say reading rejected because the tag handler failed with an overflow exception. Now we're going into the Adobe virtual machines. You might have noticed already that I'm always saying virtual machines because there are two of them. It's not like it's really easy to get one right, but you can imagine how hard it is to get two right. They're called AVM 1 and 2, Adobe Virtual Machine 1 and 2. AVM 1 is historically grown. We're going to go into the history a little bit. It's a weakly typed stack machine with support for object-oriented code. It's programmed in something that's called ActionScript 1 or 2. And something around like 80% of the stuff on the internet is still AVM 1 code. AVM 2 was later introduced. It's a ECMA 262, aka JavaScript stack machine. To my extreme horror, I discovered that the ECMA specification actually only specifies the language and not the virtual machine. So the virtual machine is again completely of Adobe's making. AVM 2 is programmed in ActionScript 3, which is close to JavaScript, which is also the reason why adoption is really, really slow. Because the people that write blinky Flash stuff for internet consumption really struggle with concepts like OOP, and ActionScript 2 and ActionScript 1 are more event handler-like programming that is more natural for web developers to develop in. I want to bore you with the history of AVM 1 a little bit because it gives you an insight on why things are so fucked up. In the first AVM 1 introduction was in Swift version 4. Before that, there was relatively little event handler type of things that you could do. The first was already a Turing-complete stack machine. It had variables, branches, subroutine calls, everything you would wish for. Interestingly enough, they decided to have all variables being strings. So if you would add two numbers, it would actually push two string representations of the numbers onto the stack and then call the add opcode. And the add opcode will try everything in its possibility to convert the string into a number and the other one into another number and then add them and then back to a string and then push